is that I was saying before. So to Sue, the exam, we do have a midterm and a final in this class, and sort of what I've decided to do is to reschedule them for next Wednesday. So Wednesday the 20th. It's an online exam. It's going to be all multiple choice. This time, when we do the final, there will be some longer type questions, but this will be all multiple choice. It'll be up for 48 hours. Take it at your leisure. If you all want to schedule a hangout and do it together, that's fine. If you just want to blast through it, it's fine. All the exam is based on lecture content and not reading content. So I'm not going to pull any like sneaky little questions that were buried in a reading. So that's going to come up on the 20th, and I want to do that specifically. It's a little bit later than I would traditionally do the midterm, but with this class, obviously we have this series in the subtlety of Stull, and it's actually it's 4 lectures. So we've done 2, and there are 2 more coming. And I want to get through those because I like having a single cohesive notion. After the subtleties of Stull, we then go into the more specifically special effects section. I think the first, I have to look at my lecture notes here. So right after we'll get into phase separation and crystallization, and then it's sort of we intermingle back and forth between colorants and special effects for the remainder of the class, like very specifically. So that's where we're going to go, and so I like to. That's sort of the dividing line in Glazes 1. It's really when we go from materials into Stull. The first time that's the dividing line. So I really like to have those conceptual breaks come. So that'll go up next Wednesday, and I think you'll have until Friday. The one difference is that there will be no gap for lectures. So there'll be another lecture that comes up on Thursday. But the last lecture that applies to the exam is going to be on Monday. We'll have a hangout on Tuesday so we can discuss any of that content and review it. The exam will go up Wednesday, and then we'll have the new class talking about crystallization on Thursday. Okay? Make sense to everybody?
Yep.
Okay. So, what questions have you all got?
Well, I'm just can't seem to wrap my head around the laying of Stull on top of the phase diagrams.
Mm-hmm.
I guess like I understand that. So I understand Stull is based on silica and alumina.
Mm-hmm.
I don't understand where. So, and then it's also based on 0.3 to 0.7. So are we assuming that it's 0.3 to 0.7 when you're plotting your points on the phase diagram?
Mm-hmm.
So like.
Okay,
yeah.
So these are all great questions. Now the first thing we have to go back and review about the phase diagram is the thing to remember is phase diagrams never address glass. Okay, and that's a really important thing to note, that no matter what, you never see glass on a phase diagram. Okay, and that's because it's not considered a phase by the definition, whereas glass is or a phase diagram is literally documenting the crystals that are created. Okay, so the crystalline species. Silicon is a crystalline species, and silicon is on the corner of all those phase diagrams. Alumina is a crystalline species, and so phase diagrams only ever address that. So that's actually the first thing that we need to remember when thinking about how we're reading the phase diagram. Okay, when we get into the notion of crystallization, okay, crystallization becomes very tricky because we are then crossing that line of sort of going, okay, well, all the glossy stuff is glass, and we can track how that is, and I talked about the glass formation boundary, which is just the line that Carty has tracked by recreating, making glasses and sort of going, where does it crystallize and where does it form glass? Okay, and so then we get this extra amorphous form inside the phase diagram that is the overlay. Okay, so that's the first part. Now, why the phase diagrams are still relevant is because at the end of the day, our glass is silica, alumina, and from a relevant crystallization standpoint, the alkaline earth. Okay? Because remember, whatever we're precipitating out in a crystal, in our matte glazes, is one of the glass formers, at least, always silica, and an alkaline earth, or whatever the representative alkaline earth is. Okay, so if we go back, so let me just find the right.
Always silica?
There's always silica.
Okay. But isn't it an excess of alumina that causes the crystallization? Or
it is, but remember, we have orders of magnitude more silica. Okay, so it's the excess of alumina that triggers the crystallization, but it still is using silica to crystallize.
Okay.
Okay, and so silica becomes the dominant factor. Okay, so hold on. Sorry, just pulling up my documents and then go into screen share, and it doesn't want to screen share. So I have to reduce my resolution. Now I go to screen share. Okay. And everybody freaks out for a second, and here we go. Okay. So going back to calcium precipitation. Okay. Everybody sees the SEM images?
Yep.
Okay. So what we have is in the upper left-hand corner, blow these out, is a northite, right? And then in the lower corner we have wollastonite. Well, we know from just reviewing our materials that the composition of wollastonite is one calcium molecule and one silica molecule. Okay.
Yeah.
We also know that a northite, well, or actually we can go. Oh, that's not the clear one. A northite here. Okay. Here's the formula for a northite: is one calcium, one alumina, two silica. Okay, so it is this excess alumina that generally forces the crystallization in the upper region. And again, this is where it starts to get tricky, and what yesterday's lecture was really talking about is that, again, we actually have multiple forms of crystallization dependent on the material. Now, again, sort of what came out today and on last Thursday is, again, the sort of lies that I've told you guys in the past, and I'm not real proud of that, but it all is in the sake of trying to jam a lot of information into Glazes 1. And so, yes, it is the alumina, the excess alumina, that forces most crystallization. But when we get into crossing into this wollastonite region, we start to see, okay, and here's the real conceptual sort of thing we have to wrap our mind around. It becomes more about this glass formation boundary, right? And the glass formation boundary separates glass from precipitating crystals. Now, the fact is, in the firing, this is all glass, okay? Everything in our composition is glass. Okay, but in the cooling, it precipitates crystals, and that actually can track with the phase diagram. Even though the phase diagram does not document glass, that doesn't mean that these materials are not melting inherently and then crystallizing on the cooling. That's how crystallization happens. Okay, that's the whole act of chemistry, that you heat a certain combination of 2 elements, 3 elements, 4 elements, and that you heat them, and then on the cooling or somewhere in the heating cycle they form a new material. Okay, and that's where we end up with the crystallization of these materials, but we can track what stays glass versus what precipitates. And so again, it's this gray area of, really, we're talking about the glass formation boundary, and it's actually the stability of the glass That's the major dictating factor, which is why we can get these wollastonite crystallizations. Now, again, that area is very, very small. We get many less wollastonite crystallized glazes, wollastonite mats, than we do the anorthite mats. The anorthite region is fairly large, and wollastonite is literally just a tiny little corner at the bottom. Okay, and so that those transitions are very defined and very consistent and very regular. But we also come into something that I don't remember how much I talk about, but creating those wollastonite mats, we have a lot of compositional problems. Okay, meaning that getting something down in that corner is very difficult. Okay, and we could look at that with again, at the most simple thing. Let me just open, and I shouldn't have stopped sharing. If we open up the glaze calculator and we come in here and we just do Neff-Psi and whiting, and we balance these for the most part 33, 34. Okay, so with Neff-Psi and whiting, this is the lowest amount of silicon alumina we can get in a stable glaze. Of course, we don't have any clay in this, but take note, our alumina level is at 0.3. So that's still pretty high for trying to get into that lower wollastonite region, that one tiny little corner back down here. Okay, so is the overlay just a conceptual exercise? Yeah, for the most part. We're taking data that we've generated. I've never seen glass addressed on a phase diagram, and it's because it's not a phase, it's just a material. It's not a crystal, I should say, which is what they consider a phase. And it is sort of puzzling. It's definitely puzzling why we're missing out on that. But anyway, I'm rambling. Sue, would you like to redirect my rambles?
So I'm confused about where you got those ratio lines, because I guess I don't understand what we're measuring. We're measuring moles or mole percentages, or if you have 0.3 alumina and whatever 1 point whatever silica, I'm trying to how do you figure out where to put? Is it all a percentage of all the materials that you have?
Well, again, another thing that is confusing is that the phase diagram is by weight.
Okay. Okay, so it's
and
a lot of...
Oh, go ahead.
Well, it's more calculations than I can just do in my head then to kind of figure out where from UMF to put it onto the phase diagram.
Right.
Okay. Okay.
There is a gap in math, and unfortunately that there's not a better document that addresses our needs better than the phase diagram. It's why that this is sort of this wonky shape, and that it's not the nice square that Stull is, because Stull is based on moles ostensibly,
yeah.
and this is based on weight. Okay, which makes the whole thing really wacky. And even drawing these, I'll fully admit, these drawings are an estimate because I do the math as best I can. But even then, when I'm going in and trying to draw these in, these are just my drawings that I created in them. Trying to get my drawings to match the exact weight base is just screwy. And that's why these don't go square. It's actually not because this is triangular, because all I am tracking here is I'm just saying we're going to take the alkaline metal as a given, because it actually plays no role in crystallization, which is what we're really talking about. So we can leave the alkaline metals out. So really that leaves us with a alkaline earth silica alumina system. And so, it's just simplifying that as best we can, knowing what we know about the glass formation boundary, knowing what we know about what crystals are precipitating, and it leaves us to this projection. Really, is what it is. It's not an authoritative position. Now, again, I would guess that your question that might come up is, well, how do I know that I'm going to make an anorthite glaze versus a wollastonite glaze? And I don't have an answer for you. You could come back and really try to figure out the math of this line. You absolutely can try that. Is that absolutely going to work? Probably not. What you can do is you can push your extremes. You could, say, do a line blend between the lowest matte you could possibly make and the highest matte as far as, like, say, alumina level. And you can definitely see that distinction. You'll see a lot of trends. A lot of the lower corner mattes really tend to run a lot more. Or they'll tend to form rivulets. These rivulets are really indicative of low silicon alumina levels because the glass starts to pull based on lack of surface or low surface area or surface tension, and we'll talk about that when we talk about fake wood ash glazes. But that we know that the two areas are separate, that you can form two kinds of crystallizations within one stall map. Okay? We've documented it. We've got those SEMs. Like, we can clearly show that. Where exactly those fall, that's dictated by the phase diagram. But, like, can I give you a hard number that says, oh, well, when you cross 0.35 alumina, that's going to do it? No, I can't.
Right.
But it's somewhere in that lower corner. Let's see, Kevin. I would say that the phase diagram is more clear to me than the stall chart. My understanding grew much more with the last video. Yeah, and I mean, it's without a lot of the background in stall. Stall becomes a little abstract. And definitely for you, go back and watch lecture 7 from the first series, where we really talk about what stall is just doing is rearranging the phase diagram in a way where we take the fluxes as set, and then we just increase silica and alumina systematically. And then you get all the different proportions therein. And that sort of gives us every variable in stall within our working temperature range within the glass formation boundary. If we went on to the phase diagram and we just kept adding more silica and alumina, you can absolutely do that. It just doesn't melt at our melting temperature, which is cone 10. Okay, the temperature just goes up, and that's the whole cone theory that was on. I guess it was last Thursday's lecture, right, where I was talking about what was actually going on with cones. Yeah. And that's just very simple. If you just add more silicon alumina, and the temperature just inherently goes up because your fluxes don't. The phase diagram tells us the same thing because you can track temperature lines in the phase diagram. Did I answer your question, Sue?
Yeah. Yeah, I was just kind of lost in translation, just like trying to match up stall with the phase diagram. So it makes more sense now that it's weight, percents, and yeah, definitely.
They are not perfect equivalents. And that again, this is my mea culpa, where I expose all the lies that I told to you, and you and I had a discussion about that, like over the winter. Like these are those lectures, because things like the 5-to-1 matte line, like yesterday's lecture, that very much comes in of that's very flexible, and I'm not even confident enough to say that that's even the higher silica to alumina ratio matte lines that I document there. I'm not even super confident saying that those are actually true either. I think it's something that we need to go back and retest again with better chemistry, really probably making her own Fritz to really hit chemistry right on, instead of a lot of those formulas that we use to make those are relying on alkali metal carbonates. And so then we get the dissolution problem and the crystallization problem, and it's just bad times all around. The fact that the phase diagrams are there is a great tool, and a lot of and I think I show them in Glazes 1, and then I say we're not going to talk about them. And this is sort of the reason why. Because you'll find a lot of Glaze classes, they'll show you a phase diagram, and they'll be like, this, that, and the other, and blah, blah, blah. And, yeah, everybody ends up sort of where you are. And they're not even imposing Stull on it. But the ability, and actually the really cool thing that I love about this lecture, about yesterday's lecture, is the notion of using it to look at all the different types of matte glazes we can create. Okay, because that is a huge deal. Because if we go, I was talking about this with my students in my the weekend classes I'm teaching right now. Of you sort of go, well, okay, to them, you've got a matte glaze and a gloss glaze. Okay, well, we automatically know that you've got a matte glaze and a gloss glaze. So that's two types of glazes. And we were trying to explain to them, they had this glaze that we were running analysis, and there was this glaze listed as a matte. And I'm pulling the chemistry, and I'm like, nope, not a matte. And then we go and pull the test tile, and not only is it not a matte, it's totally a gloss, and it looks like a gloss. It's just someone else's different definition of a gloss. It's a low sheen magnesium gloss, and we know that magnesium just doesn't melt super level, super flat, so it's got a lot of surface roughness, so you don't see that type of variation. But then we come into the mattes. Okay, well, we've got 2 mattes per RO, okay, as documented. In all the phase diagrams, they all cross 2 different mattes per RO, even down to talking about the zinc. And zinc will come up again in the special effects, and we'll talk about that gonite willemite line. And that's a super important line because, again, we're taking advantage of one of those lower region mattes. Okay, the low alumina, because willemite is a zinc silica crystal, and that's what's so important about the crystalline glazes. These crystals, right? These are just zinc and silica. This is not an alumina-based crystal. Okay, and if you go hang out with the crystalline people, they'll be all obsessed with their alumina levels, and they'll go, oh, you have to eliminate all the alumina. Well, what I've sort of found is that that's not true. Do you have to eliminate a lot of alumina? Yeah, but again, you can push it up to the edge of that phase field. And actually that's very well defined for the zinc glazes. I found that at 0.25 alumina via UMF, that is the phase separation, the phase field separation. Okay, so you go over that, and you're forming gonite. And you're underneath that, and you're forming willemite, and you get these. But when you look at the UMFs of crystalline glazes, they're all like 0.05 alumina, 0.1 alumina. And they don't have to be. You can still make crystals with higher alumina levels. So doing that, okay, so we've got the 2 types per RO. Well, we know we've got magnesium, calcium, strontium, barium, and zinc. So that's 10. And as we started to talk about today, we can also add in iron and manganese. That's 14. Okay? But then the crazy thing is you can mix and match, all of these and get all of these different variations on texture. And that's what's so sexy, and that's what I think is one of the major untapped textural things to do. Okay? And we know that it's a thing because that's matte glazes we're famous for. If you guys don't know Val, Val was a professor at Alfred who retired in 1997, and he used to teach my course. And I mentioned his book. Cushing's Handbook is his self-published all-around ceramics book. But he did a lot of glaze work. He taught glaze calc, but he was famous for these sort of buttery matte glazes. Well, if you go and look at his matte formulas, he was using dolomite like there was no tomorrow. What's the thing about dolomite? Dolomite is 1 calcium, 1 magnesium. Well, he's splitting his RO, so he's forming 2 different crystals, which gives you a different texture inside his matte glazes, and just gives you a nice, buttery, diversified crystal texture. And that's what's so cool, because now, let's blend strontium and zinc and see what you get. Because as we will talk about later, that the major effect of RO is in color. Okay, and again, it's this thing of, I don't mean to negate the alkaline metal. Lithium and sodium and potassium are very necessary for getting our melting temperature down. But when it comes to color and texture, it's all about whatever the dominant flux is in our system. So if our glazes were pure sodium, that would actually be influencing color and texture. But since it's predominantly calcium or predominantly alkaline earth, that then becomes the dominant influence and creates our color and reflection, our color and our texture. Yeah, it's cool stuff.
So you've got phase diagrams for the alkaline metals as well, but those don't. Is it just because the RO is dominant that those don't actually come into play?
Yep.
Okay.
And you can see, so let's just pull up let me screen share here. Pull up the sodium one. I mean, we already talked about this in the lecture, but so here's the sodium one, okay? And we've got nepheline, which we are somewhat familiar with from nepheline syenite. And here's albite, and if you recognize the formula above it, you've got Na2O Al2O3 6SiO2, which is the formula for the generic feldspar. And then you've got down here sodium silicate. Now this is very, very interesting. Okay, so basically, if we sort of project that the phase or the glass formation boundary sort of comes through nepheline and then goes into sodium silicate. Well, if you guys are at all familiar with sodium silicate, I don't talk about it very much, but it is actually a sometimes used ceramic material. And one thing that you might know that sodium silicate is used for is to make a material called water glass. And it is literally a type of glass that'll just precipitate in a water bath. Really what you do is you make a saturated sodium silicate solution, and then in any saturated solution you are constantly precipitating out crystals. Crystals are just falling out of the saturated solution and crystallizing on your material. And actually, I know if you go into the readings from class 1, those kids books that I have in there, if you read the one on sodium, it talks about sodium silicate. But here's what's interesting. Why we don't do that, and this will come up in the next lecture, the one after, is because of the question of glaze durability. A sodium silicate crystal is terrible from a durability standpoint. It dissolves in water. So even if we precipitated this crystal that was based in sodium, it would actually fall apart from daily use, and shockingly enough, that is literally... that comes back to, my terrible lemon test. This is essentially a high sodium glaze, and yeah, it's based in silica, but it fails because there's too much sodium, and sodium silicates are weak bonds. Okay, easily dissolved by acids, by water, by all of that stuff. So again, that even goes all the way back to, why do we use 2 fluxes? We could make a glass that is just sodium fluxing out silica, and it sucks. Okay, it does no good. It does no good for glass blowing. It does no good for pottery or dinnerware. Okay, that's why even blowing glass and window glass is soda, lime, silicate. Sodium, calcium, and silica, because that combination gives us physical strength. Sodium, it'll flux your shit, but it makes it terrible. And this is going to be the interesting thing that we'll talk about in the very last class, is when we talk about what's going on with Cone 04 at very, very low temperatures. What are people really doing to make glazes flux? So, mostly we're talking 1300, but Cone 04 is about 1075. So, we're 225 degrees beneath that C, and that's a major temperature jump. We're beneath the cone 011 line. We've now gotten to this point. And a lot of the times, what people are doing is that they're making really shitty, basically, forms of sodium silicate or lithium silicate. And they're all terrible. And in glass blowing, we see it all the time with acid etching. Okay? Actually, my glass tonight is not that etched, but, I always have my iced tea glasses with me. And generally, they're pretty terribly acid etched because excess sodium really makes it weak. And I'll, just sort of say what will come up again in the later lecture. But the whole process of glazes becoming weak is super simple. And it's this whole thing called ion exchange. And very simply, it's take a brick wall, pull out a brick, put in a Lego. Okay, and you just keep pulling out a full-size brick, and you put in a Lego, and you do that enough, and the whole system crumbles. Okay, and that's what you do when you have excess sodium in your glasses. And that's, the whole thing about food safety. Everybody gets in a twist about food safety, and you guys know me for the most part, and not that I don't care about food safety. Food safety is a very serious issue, but I would much rather talk about glaze durability and the way that affects food safety. And glaze durability is super easy to define because the number one cause of glaze failure is excess R2O flux. Okay? Because excess R2O flux, excess alkaline metal, causes this ion exchange to happen. Where, because remember that when we're talking about that brick wall, okay, you're pulling out a full-sized, 9 by 4.5 brick, and that's a sodium molecule, and you're inserting a tiny Lego, and that's the hydrogen. And acids are based in hydrogen, water is based in hydrogen, okay? And they'll switch. They will absolutely switch. Do not forget that the alkaline metals go hydrogen, lithium, sodium, potassium, and vinegar and bases are all based in hydrogen. Okay, so they will more than happily ion exchange if you're creating a weak glass, which is inherently a sodium silicate. And anyway, I'm getting ahead of it. This all comes up later. Let's see, from Kevin. I was very interested in the lithium silicate part of the video and low-fire glazes because I was looking into glass glaze paint. Are we moving towards the molecular bond in detail? Yeah, it comes up. I mean, I address actually this tile I keep waving around. Comes from my story. I sort of teach everything in stories. But we'll talk about that. But it doesn't even matter if it's lithium versus sodium or potassium. The balancing and strength is all the same from a molecular standpoint. You have to have certain things. And again, so the thing that becomes really important, and we get into this in depth later on, is again this balance in our fluxes from Stahl. Okay, in Stahl, we have this 0.3 to 0.7 ratio. Okay, and that is we have 30% of our fluxing molecules are coming from alkaline metals, and 70% is coming from our alkaline earths. And we'll get into the documentation of why that's so important, but the short answer is it doesn't matter which alkaline metal and which alkaline earth you use. Okay, it's just that 30% can be from alkaline metals and 70% can be from alkaline earth. And if you exceed that, especially with excess alkaline metals, the system falls apart. Okay? Because you start to do that ion exchange thing. And when we talk low temperature, when we get into very, very low temperatures, we will get into that because that is, that's the number one problem. And that this was a functional glaze, that I had a graduate student who used this in their thesis show, and they had taken my class, and she still did not check her shit. And use that glaze, and it was a disaster. But we definitely get into that. I'm sort of going off on a tangent, but yeah, we'll talk about the lithium and the low temperature as we go. Sorry, was I ranting? Sue's smirking.
No.
Are there more questions? You weren't smirking? You can smirk. I don't care. I have small children. I have no ego left. I get confronted with, Dada, you suck. No, not that bad. Anything else?
Well, you know your 3D phase diagram
Yeah.
thing?
Yeah.
So, yeah, my question was like the part, like those humps represent temperature, right?
Mhm.
And so above that, the negative space above that is liquid. Is that right?
You mean just this?
Like, yeah,
No.
like those are the temperatures at which the crystallization
No.
happens. Like,
The phase
no, okay,
diagram is phase diagrams are dictating melting temperature. Okay, at which
right.
point the crystal breaks down and becomes amorphous. Okay,
Okay.
and this one is actually it's a little bit it's got a dead fly in it. It's actually a little bit confusing because this is a alumina, silica, calcium phase diagram, because if you actually look at calcium, the actual pure the melting temperature of pure calcium oxide is like 2500 degrees C. It's actually crazy hot. So that's actually the hottest individual thing. As soon as you break it down with anything else, the temperature just drops precipitously, as you can see here, just like right, very very quickly to almost the lowest point in the phase diagram. Right. So here's the high point. If I could get in focus. Here's the high point of calcium, and then there's the lowest eutectic right down there. No, not that far away. So the space above it is just nothing. Okay, it's literally what temperature this material melts at. So again, if we come back to
Right.
calcium's like 2500 degrees C, pure alumina is 2000 degrees C, and pure silica is 1700 degrees C. Okay, and it's literally if you take just silica, just straight flint, and you have a kiln that goes to 1700 degrees C, you can put it in there and it will form a glass. It will just naturally form a glass, and that's the melting. And then we get into this whole question of what's not in the phase diagram of that thing of glass being a supercooled liquid, which we've already talked about how it's not, just being an amorphous solid, and that's the difference of amorphous means random versus crystalline solids, which have the repeating structure. So this is the
Oh,
point at which the temperature at which the material would become amorphous.
okay.
Okay,
I get
but
it.
on crystallization, will it stay amorphous is a different question. Now, silica will stay amorphous, okay, when you cool it. Calcium and alumina will actually reprecipitate out as a crystal. And then when you blend them, each one of these different regions forms a different crystal based on how much of the component corners are there. Okay, and we see it's called silica glass or quartz glass all the time. They will put that of course, as everything is always referenced in ceramic science, the space shuttle's windows, okay, are pure quartz glass because to get that glass to melt again, it would have to be 1700 degrees C, and re-entry on the space shuttle is, I don't even know what re-entry temperature is on the space shuttle, but that the windows are on top and the re-entry is from the friction on the bottom. Uh, Sorry, now I'm Googling space shuttle re-entry temperature. See, they're saying that the tiles only reach 1650 C. Do you guys know why the space shuttle tiles get hot? No. It's actually pretty cool. So in space, there's no molecules, right? It's a vacuum. They're all dispersed, right? So there are no molecules in space. And as soon as we enter the atmosphere, the space shuttle or some sort of space thing, okay, it's now suddenly hitting molecules, just of anything, of what's ever in the air, nitrogen, oxygen, ozone, whatever. And so the space shuttle, I'll just keep saying space shuttle even though it's anachronistic, the space shuttle is basically falling down through there, and it's slowly encountering this air. And that air has to move aside for the space shuttle. But the problem is that the shuttle is falling faster than the molecule can move aside, It's friction. And the friction generates the heat, these massive temperatures that they talk about for the space shuttle. Dumb aside, but you learn something new every day.
Cool.
From nothing to something. Next questions?
Anybody else?
It's okay if you don't have a question, Abby. It's just nice to have you here. Are you feeling okay, Abby?
Yeah.
Are you following along with all of our ramblings?
Yeah.
Okay, good. You're going to blow everybody's mind when you get back to school, I'll tell you that.
So I have a question for you, Matt.
Sure, Phyllis.
All this is lovely and theoretical and esoteric.
Mm-hmm.
How does it work in the studio when you don't have access to scanning electron microscopes and you haven't the vaguest idea if you formed this or that or the other thing?
Well, it's there.
Well, I know, but that's cold comfort.
No, it's
No,
not.
a lot of things are there. So how do I use it? How do I make all of this truly useful?
Well, that comes down to an aesthetics question.
Mm-hmm.
Okay. Some of these things, say we're talking about all these different textures of matte glazes. At the end of the day, you have to go out and try these different combinations in your studio and see what is a lovely texture and what looks like cat puke. Because just because they exist doesn't mean that they're beautiful. My wife and I were joking about, sort of undergraduate art students and that thing of that they think that everything is wonderful just because they make it. They don't have any critical analysis of going, yeah, just because you make it doesn't mean I have to care about it. It does, what it comes down to is this ability, well, first of all, we're sort of learning critical thinking about glazes. You have the ability to go and pick out a formula and go, this is good, this is bad, I like this is going to work, this is not going to work, and here's how I solve this problem or make this alteration. That's the sort of greater aspect of that. The next part that really what we're getting into and what you're asking about is how you use these tools for development.
Mm-hmm.
Okay, and it'll start to become more realistic and probably more pragmatic to you when we get into the discussions specifically about color and texture, which is where people really, or color and effect, where really people will take advantage of this because the color reactions become very clearly defining. And we talked about it briefly in one where the different reactions you get in chrome, or the different reactions you get in nickel, and sort of taking control of your glaze palette. But what I would encourage you to do, and where I think that the real power lies, is also using that same knowledge for texture. Is it something that just leaps out and grabs you? No. You have to go out and develop these things, and that's the hard thing for me even. I'm currently working with somebody who's developed a machine to make glaze tests. And right now we're talking about doing this massive series of glaze tests where our first pass is 1,200 glazes. Because the machine does them, because there are all these things that we have that aren't defined. Right? And so, it's like I often get this, people will throw the accusation at me as, oh, you're just talking theory and these aren't real glazes, and this isn't. No, these are absolutely real glazes. They're just not developed yet. And so what I'm sort of saying to you guys is, here are the parameters for the things you can go out and create. And that's where you use the technology, for lack of a better term, combined with creativity of what colors and textures, what reactions and temperatures can you create. And that's where I'd say you can go with it.
Well, I understand that, and I'm just exceptionally pragmatic, and I'm sitting here thinking, looking at all of this, which is truly lovely and amazing, and then I'm thinking I go downstairs to my glaze room and pick up all those powders and I make something, and how do I know that I have formed this kind of crystal versus that kind of crystal absent the scientific tools to let me know that with certainty?
Well, you can define that in your studio. If you go down, and as I said earlier, of go and let's just take two. We'll just say you're going to work with barium, for lack of better example. The parameters that are set up that hopefully that you're sort of coming to wrap your head around is that if we go back to Stull, right? Stull is easy because it starts at 0. Okay, and as I just sort of was, doing the calculations, that we really pragmatically are starting at somewhere around 0.3 alumina. That's our realistic lower level. Okay, and so what you could do is make a line blend. Okay, and I will show some line blends like this as a little bit later in the class, where you go from 1 point lower on Stull, and you transition to a higher alumina level, but you know what transition you're doing. It's not a shot in the dark. You know you're staying within matte formation boundaries. You know exactly what is the chemistry that you are creating. And so you make a line blend and see all the variation in there, and you'll see the transition from one textured matte to another. Okay, so it comes down to that level of development. Now, if you don't want to do that in your studio, you can go in and go, oh, well, here's this glaze, and it's a matte glaze, and its alumina level is going to be 0.5, and it's calcium, so I know it's a northite, right? You can just know that and be super smart and impress your friends. But to use it to your advantage, it's just sort of taking the parameters that you've generated and going, I know that the variables are this. I know the variable is, say, moving from here to here, and with these silicon alumina levels, and I know that this alkaline earth flux is my defining factor, so that you are inherently creating this crystal or that crystal. And going back to the calcium level, or to calcium as the example, I know it's either wollastonite or a northite. And I know that a northite only comes in glazes higher alumina levels, and wollastonite only comes in lower. And so you can start to define that and work with that. Does it make you anything but a smarty pants? Well, it just depends on if you want to pursue that for the things that you can develop. Hold on, there's a question from Kevin. Sorry, it all comes as one wall of text. Now I have to go back and see where I started. Okay. I wasn't aware that subtraction of alumina caused so much movement. I know that very strong glass bonds are formed with magnesium in it, with examples like a smartphone screen or protector. The functional glaze issue seems to be the same with color across the board. How hard can you make clay with just the application of glaze glass, and can you build forms with just glaze? Let's see. So there's several questions in there. To the alumina question, yeah, alumina is a big deal in glazes, and I think that might be the defining variable that's not in blowing glass, because you're just inherently not using alumina, and in blowing glasses you don't want them to crystallize. And there's plenty of compositions of glass that will crystallize. The one that always comes to my mind is years ago I was working on a bioglass project where we were making glass that was being used for inserts in bones. And this glass was it was a high calcium glass that was actually supposed to be inserted into a bone and then dissolve, and then bone would grow around the glass structure. So the glass was actually made to dissolve, and much like I was talking about, making this glaze that's weak to dissolve, they were actually using that to its advantage, and that bone would grow around the glass structure. So you do that by having excess calcium, and you're forcing something to crystallize in a glass. But in blowing glass, you don't want that to do it. This is probably the difference. Well, this is literally the difference between glass and ceramics, or glass ceramics as they call it, is forcing crystallization inside of glass. So yeah, alumina becomes a very big deal for us, but for you, not so much. The magnesium. Well, that's the ion exchange, and it's not magnesium. It's sodium and potassium, and that's that brick wall thing. And sorry, I teach so many classes, I forget where I was saying it, but that that the ion exchange takes place. Actually, I think it was in my Glazes 1 class last week. So, you have the brick wall, and you take out the regular brick, and you put it on the Lego, and that makes it weak. Well, you can actually do the opposite, where you take out the brick, and then you insert a larger brick that perfectly fits into that structure. And it's also called ion exchange, but that's what makes Gorilla Glass. Okay, Gorilla Glass is made with a sodium fluxed glass, and then they actually put it into a molten potassium bath, and they ion exchange in the same way. The sodium comes out, the potassium goes in, and that potassium is a larger molecule, and it locks up that glass and makes it strong. So it's not magnesium, it's actually the alkali metals, because they are easy. Because again, hydrogen, lithium, sodium, potassium, cesium, rubidium, they all do this to different degrees. It just depends on if you can lock up the glass, which is what the balance between the sodium and the calcium really define. So let me go back to the last part, to the functional glaze, the color. How hard can you make clay with the application of glazed glass, and can you build forms with just glaze? Yes. How hard can you make it? That's a very relative question. It's generally considered that a glaze is a compression coating. So, you have this pot, which the clay, like good clay is nice and it's consistent and homogeneous and has no flaws and errors. A nice piece of porcelain, even though this one has a crack in it. But the clay still has air pockets that were there from the forming process. It still has lack of homogeneity. So we put glaze on it because glaze creates an impervious, homogeneous, evenly melted glass coating, which we call a compressive coating. So it's like, like putting on a big bear hug, holds it in tight and keeps it as a unified mass, which, like blowing glass, it already is a unified mass because it theoretically shouldn't have any air pockets or anything breaking up the homogeneity or the strength. Does glaze really make it stronger? That's up for debate. Something that I always talk about, or that comes up a lot, and we'll talk. Actually, it comes up later. We talk about silicon carbide. Like this, actually, this is what my iced tea sits on. But this little trivet is a piece of silicon carbide, which is a very, very hard material made up of silicon and carbon, shockingly enough. And what this was is we were doing experiments for a body armor company of actually putting glaze coatings. So this is actually a glaze on top of silicon carbide, which is actually something that's super hard to do. And now it holds my iced tea. And the notion that they wanted was to put a compression coating on the silicon carbide because it was being used for body armor, military-grade body armor. And the thought was if they put a compression coating, it would make the body armor last longer because the standard is that body armor in the field has to take 3 hits from our own sniper rifles, from our own most powerful sniper rifles. And the silicon carbide stuff can take 2 hits, but by the 3rd hit, it doesn't really hold together anymore because it's just a bicycle helmet. It just if you shoot body armor, ceramic body armor, it shatters. That's the whole point. Just like a bicycle helmet, like they're all just styrofoam in a plastic case, and when you hit your head, it just shatters. It just turns into popcorn, and that the shattering actually dissipates energy. It never really worked though with the silicon carbide. So there is some benefit. Like I couldn't give you a percentage off the top of my head, but yeah, it inherently does because clay is not as homogeneous as glass. There's inconsistencies in air pockets, just because most, it's not mixed very well, and you're trying to pack all these molecules together, and that inherently has negative space. Good questions though, and I'm sorry, Phyllis, did I answer your question?
Yeah, but we know that STEL, based on what you've told us, only applies to potassium, calcium, cone 11. And I think you and I briefly chatted about that this winter when I asked you whether or not there were other diagrams out there that in lieu of calcium had magnesium or any of the other alkaline earths. And I think you said no, if I recall correctly.
No. There are, and that's what came up in today's lecture. That those maps, those colorful maps that I showed, are the ones that I have created. That is literally the work that I did in the lab of recreating Stull with the different fluxes. It doesn't. I don't have all the legends drawn in of matte versus gloss, but it's just sort of left to your imagination to go. Well, we know that mattes are in the upper left-hand corner, and that underfired is in the lower right-hand corner. So that is the manifestation of that. It's not something that anyone besides me that has put any work into, and for me, I'm always on to the next thing. As to the question of temperature, that's a hold on. That's a we're getting there. Because that is the very big topic, and that is going to be next Monday's lecture. Is specifically about how Stull applies to temperature, because I'm working with someone. Actually, this project of with the glaze making machine. That project, I'm also working with Derek, who runs Glazy.org, who does this amazing visualization of data. And he and I and Andy Brayman, who built the machine, are working together to try to change the way that we visualize temperature. But at the end of the day, Stull really sort of works. I mean, it's like, let's say I was just at the state park over the weekend, and there are all these classic cars, and you look at all these classic cars and like, yeah, do we have better classic cars that do things better? Yeah, but it's still literally you take gasoline that turns a crankshaft and that makes the wheels run. That inherent model doesn't really change, but we definitely have better visualizations. It's just I'm the one doing all the work, and I haven't gotten there yet. I always want to do the next piece of research instead of going back and doing the analysis. But it's coming. It's coming. I swear. It's just I got a lot of shit to do. Oh, sorry. Didn't mean to swear. Oh, what's Kevin got? I'll make you big since you don't have a microphone to kick in your. Okay, you got a plate. I see. It looks like phase separation, but you're a little out of focus for me. Let's see. I have this piece of clay and glass frit that my friend Philip Yanella made. I know that name. Do I know Philip? And I'm very interested in the process. He made it sound easy. Yeah. I mean, I assume he's just melting glass into a plate. Yeah, it can work. What I would say is wait until tomorrow's lecture or Thursday's lecture. Because what it comes down to is this question of thermal expansion, which is what the next lecture is all about. Thermal expansion is a huge, huge deal that is not very well understood. And honestly, probably the fact that plate survived is just lucky. Because is the process easy? Yeah, but the whole thing is in sort of not to talk about the whole lecture ahead of time, but everything has thermal expansion. Okay, everything expands or contracts when you apply heat to it. The problem that we have in ceramics specifically is that clay and glazes have inherently different thermal expansion. And if materials have different thermal expansions and you physically bond them together, and glaze is physically bonded to clay, the twain shall never separate. They are rock solid because when they cool, they're just stuck together. So when you get something like that with a big pool of glass in the bottom, where is it? My wife's got a tile here somewhere. I can't find it. I got too much crap around my house. When they cool and physically bond together, the clay has one thermal expansion and the glass has another. And when you've got a big pool of glass like that, very likely it can lead to the plate cracking. Obviously, things survive. That survived. I've got lots of things that do survive. But I couldn't see. Is that thing crazed? Do you know crazing? Is there a network of cracks through the plate, through the glass? That is, we would call it crazing, but that's thermal expansion mismatch, and that's actually the glass cracking to relieve the tension of thermal expansion. if those cracks were big enough, they would just snap the plate in half. And that's what Thursday's lecture is going to be all about. Yeah. Because I think I end today's lecture saying, we'll talk about thermal expansion, or I forget when it comes in. Sorry. But yeah, so Thursdays is definitely all about why thermal expansion happens and how we control it. You can do it. They're always going to have those types of cracks because glass. Well, I shouldn't say always. You may be able to engineer a clay body that has a thermal expansion that would match the glass like that, but it would probably be a shitty clay. Oh, sorry, I keep swearing tonight. Sorry, I have a potty mouth. Yeah, but that's a good one because that's Thursday's lecture, and then and then Monday we do talk about temperature and glaze durability. They are one in the same. Yeah. Any other questions? No, Phyllis, you good for tonight?
Good enough.
Good enough. Well, I can answer more questions.
They're in the unarticulated stage in my brain.
Okay.
Just trying to gather all this stuff in.
Well, like I said, yeah, right. Make it useful. Well,
making it useful to me, like in one when you were talking about 0.3 to 0.7 and all the not boundaries, but concepts you set forth, they made sense, and I could go from those. The phase diagrams, well, they're beautiful. Aesthetically, they're absolutely beautiful, but they just kind of don't jump down into my glaze room as easily as did those other little numbers. So that's where I'm having transitional issues. But that's all right. It will come to me.
Yeah, I think probably what would be best is for you to just make up a few compositions on the calculator of just make up a matte glaze that's fluxed with barium, make up another one that's fluxed with strontium, make up another one that's fluxed with calcium, one with magnesium, and one with zinc. And literally just keep the silica level the same, the flux ratio the same, and try those, so it's all the same, and then see what differences in texture you get. And I think that might be a more clarifying standpoint because like the lithium, that's not even the matte glaze, the barium mattes are super buttery, and the calcium mattes are a little chunky, the magnesium mattes are a little thick, so they have all these variations in texture that you get based on using the different ROs. But the importance of the ROs will also come in as we get into color. So I think you'll find more relevance in it, but don't give up on the notion of sort of what it's more about understanding the variations in matte glazes, right? That's what we really can derive from it. Sort of take that and gestate, and like I said, I mean, this is definitely the in one, I think the hard part comes in the second half, and in this class, the hard part comes in the first half, and then all the fun stuff comes in the second half, because we're really leading up to, why do the alkaline earths specifically have an effect, and what that effect is, and then we get into how do we take advantage of that effect. That's sort of what part two is.
And I did tweak with some of those things because I was most intrigued with your statement in one when you said barium glazes can be shiny. And I thought, really?
Yeah.
And
again,
so
in the classic. Shine on
so I played with that and got some lovely barium glazes, and then I started thinking, well, does barium, so barium turns copper turquoisey, but what does it do to the other transition metals? Does it have an effect on those? And so I started playing with that. And then it was like, well, what do barium and magnesium do together, since I really, really, really like magnesium? So that was kind of another area I started playing with. I mean, just started.
Well, and that's great. That's exactly where I would want you to go. So you're on the track.
It's just when I was looking at those diagrams, I thought, really, really, Matt, you're pulling a Cardi on me at this moment, right?
Oh no! Because he would throw that to you in the first week.
Ah.
No, well, that's the thing, and I always say about Cardi is guys who don't know, Cardi is my mentor. He's he teaches this subject in the engineering school. He's the smartest man I know. I mean, by far, he's an absolute genius. And so the things that he teaches cannot be avoided. My thing is, I always say I'm just translating it for different types of thinkers. Because it's very straightforward and analytical. So, he'll teach phase diagrams. You can't avoid it. But he'll literally go, this is the phase diagram, here it is, deal with it. And that'll be the first week of Glazes. And, I don't want you to go there, because then everybody gets left behind right off the top. So.
Right.
But don't worry. It all will become clear as we go.
Oh, I wouldn't worry in the least about things like this. There's bigger things in my life to worry about, I'm sure. But
good.
I give up on it. I've given up on worrying. It has no value.
Yeah, it's true. Unless it involves my child running around the neighborhood naked, which does happen, I wouldn't worry about it.
Oh, that's great.
Yeah, she's very proud. Hold on, wait, I got a question here from Sue. Why have you got? Okay. If you have two or more RO sources, do they precipitate their own crystals of silicon aluminum, or do they combine to do a new type of crystal like dolomite? As far as I know, it's two types of crystals, but side by side.
Right.
I don't believe it is a single crystal, because that's a fascinating question, Sue. I don't know the answer. I'm going to stop talking because I don't know.
Okay.
That's worth looking into. Those types of phase diagrams don't exist to my knowledge, so no one's gone in and done. Because the whole process is, that they create these samples in the lab, and then they go in and they run them through X-ray diffraction, and X-ray diffraction tells them, what they have. I don't know. Great question. Either way, it's a new thing. You're either getting two types of crystals making a new thing, or you're getting a third type of crystal making a new thing. So.
Right.
So, where on the West Coast are you?
Victoria, BC.
Ah, lovely place. A little bit. I'm down in Portland. A little bit far from Portland.
A little bit. I'll be in Portland in March.
Of next year?
And Sika.
Yeah.
Oh, well, I'll be in Portland anyway.
Nice.
And there will be much rejoicing.
There will.
Alrighty, folks. Should we sign off?
All right. Yeah.
Cool beans. Okay. I will see you
Matt.
guys. Yes.
Thank you.
Oh, you're welcome. Happy to. I'll see you guys all next week. The one thing I will say is next week it will be my last meeting before the trip, so we need to think about how we want to do it. Like I said, I'm more than willing to do the 2 a.m. meetings, but if people have any flexibility or lack of flexibility or any of those types of things, hopefully I'll be verbal at 2 a.m. in Holland. Yeah. Okay. So we'll all brainstorm on that, because I still don't have a great answer except for 2 a.m. Okay. I'll talk to you guys next week.
Bye-bye.
Okay.
Bye.